Welcome to Sable Island Conference 2021, a series of virtual presentations about the natural wonders and human history of this fascinating island. We are especially delighted to acknowledge the Dalhousie Coastal Hydrology Lab as the sponsor for this session. Session 9, Freshwater, Afloat at Sea, integrating traditional and wireless monitoring techniques on Sable Island to reveal freshwater vulnerability, is being presented by Julia Cantelon. I am April Hennigar, Chair of the Board of Directors for Friends of Sable Island, a volunteer-run charitable organization dedicated to the long-term protection of all things Sable Island. We've been holding a biannual conference since 2015 as a major fundraiser for our education programs, and especially our annual scholarships. We had hoped to hold it in person for 2021, but this proved too difficult with the pandemic restrictions. So we are happy to present Sable Island Conference 2021 virtually. Precariously located in the northwestern Atlantic Ocean, Sable Island has limited freshwater resources. Small surface water ponds that support the island's unique ecosystem are sourced from rain and snow into a freshwater lens, a lens-shaped freshwater zone that floats above denser seawater in the island's permeable sands. This freshwater supply is vulnerable, especially to storm impacts like flooding and erosion. Today, we will learn more about current research on this life-sustaining resource. Presenter Julia Cantelon is a PhD student candidate at the Center for Water Resources and Department of Civil and Resource Engineering at Dalhousie University in Halifax, Nova Scotia. She is a member of the Dalhousie Coastal Hydrogeology Lab, and her work is supervised by Dr. Precariously. In 2019, she completed her Bachelor of Science in Environmental Science at Western University in Ontario and joined the Dalhousie Coastal Hydrology Lab for her project on the precarious freshwater resources of Sable Island. Her work focuses on monitoring and modeling the fresh surface and groundwater resources of Sable Island and the influence of a changing marine environment. Thank you, Julie. Over to you.
Good afternoon, everyone, and thank you for the introduction, April. I'm excited to have the opportunity today to talk to you all about the recent research that I've conducted on Sable Island's freshwater resources that are afloat at sea. Today, my talk, as April mentioned, will be discussing how I have applied traditional and novel wireless monitoring techniques on Sable Island to monitor the island's present and future freshwater vulnerability. As April mentioned, I've conducted this research as a member of the Dalhousie Coastal Hydrology Lab with generous support from my supervisor, Dr. Precariously, and my committee member, Dr. Scott Ketchison from Athabasca University. I also want to take a moment to recognize the agencies who have supported this work and made it possible. We have received significant funding from NEOPAR and significant in-kind support from Parks Canada Agency, which has made this research possible. We are all here today because we have a shared interest in Sable Island's unique physical characteristics and its ecosystem. But before I dive into the specifics of my work on Sable Island, I wanted to take a brief moment to highlight the global relevance of the work that we are doing and the unique opportunity that we have to study these issues that are relevant all around the world on Sable Island. Globally, small islands host dense human populations and very diverse ecosystems. Approximately 700 million people live on island environments worldwide, and this number is increasing rapidly. In a special ocean and cryosphere report, the Intergovernmental Panel on Climate Change emphasized the risks to coastal zones and cold regions. This figure up in the upper right-hand corner highlights that there's a high level of additional risk to coastal zones from climate change impacts. Comparing the risk across different cold region and coastal regions, it is clear that islands are one of the most vulnerable regions to anthropogenic climate change. These risks from anthropogenic climate change are further exacerbated by risks to freshwater resources. As April mentioned in my introduction, island environments are completely surrounded by seawater and have very limited freshwater resources. As such, island populations and ecosystems rely on a fresh groundwater lens, a lens-shaped freshwater zone that is sourced from infiltrating precipitation that floats above denser saline groundwater. This fresh groundwater is a life-sustaining resource, and the presence of this resource often determines the habitability of a small island. An island's freshwater lens is hydraulically connected to the ocean in a very delicate equilibrium, and therefore changing marine conditions and climate conditions threatens to disrupt this delicate hydraulic equilibrium and impact the available fresh groundwater that supports island ecosystems and populations. This can occur through three main mechanisms. First, changing precipitation regimes can reduce the volume of fresh water that is available to infiltrate into the subsurface, resulting in a thinning of fresh groundwater lenses. Similarly, rising sea levels can cause saline groundwater to extend further inland and reduce the volume of fresh water. And finally, climate change can result in increasing numbers of large storm events that can flood the land surface and infiltrate and contaminate fresh groundwater resources, reducing the volume and quality of available fresh water in island environments. These aforementioned changes describe the process of saltwater intrusion. Saltwater intrusion occurs when seawater encroaches into previously fresh groundwater. On Sable Island, we are looking and focusing on how these large storm events are causing saltwater intrusion and significant morphologic change, and the connections between these processes and the impacts to surface and subsurface freshwater resources. Just to briefly explain the process of vertical saltwater intrusion from these large storm events, I just wanted to briefly go through this figure. So large storm events can breach coastal barriers and cause extensive surface water flooding. These coastal floodwaters are able to inundate into the land surface and cause seawater to infiltrate into these previously fresh water resources that are found along the coast. This fresh water salinizes the seawater salinizes fresh groundwater that is found along these coastal environments, and it can cause dramatic patterns of salinization in the subsurface, as shown in panel C of the figure here. However, after these floodwaters ebb, these patterns of salinization in the subsurface are still present, and it is persistent far beyond surface water flooding in both space and time. Gradually, background fresh groundwater flow from fresh precipitation is able to flush the seawater back out to the ocean over months to years, as shown in panel D. Now, this represents a highly simplified situation for vertical saltwater intrusion. In the real world, these coastal landscapes are complicated, and the situation is not so simple. Incidents of erosion in association with large storm events can complicate patterns of vertical saltwater intrusion. Additionally, multiple events that occur one after another can cause multiple plumes in the subsurface. Topographic variation can cause seawater to pool and increase incidence of vertical saltwater intrusion and the amount of seawater that can infiltrate into the freshwater. And heterogeneity within the subsurface and the presence of human infrastructure such as wells can further complicate the process of vertical saltwater intrusion and can impact and prolong these incidents. On Sable Island, we are focusing on the impacts of these large storm events and how erosion, saltwater intrusion, and multiple events interact with the island's topography and can impact the fresh groundwater resources. Sable Island is an ideal site for this because it has very limited anthropogenic influence and very uniform geology. So we are able to study some of these coastal processes without too many interacting factors. As we all know, Sable Island is a very small, remote, sandy island 150 kilometers off the east coast of Canada in the northwestern Atlantic Ocean that is designated as a Canadian National Park Reserve as a result of its extensive human history and its unique ecosystem. And this ecosystem on Sable Island and Parks Canada operations on the island depend on small surface water ponds that are present on the island and the island's fresh groundwater lens. So the previous facts that I've mentioned make Sable Island an ideal island groundwater observatory, as it is relatively pristine site because of the fact that there's limited anthropogenic influence on the island as a result of its remote location and its national park status. Additionally, Sable Island has a very long time series of historical environmental monitoring data that is invaluable for assessing long-term change in the surface and subsurface freshwater resources. The presence of long time series of historical environmental monitoring data that we have on Sable Island is unique and allows us to assess long-term and short-term changes that are occurring on the island with respect to large erosion changes, morphological shifts in the island, and large storms. Finally, Sable Island is located in a precarious ocean location. It is in a national and global hotspot for sea level rise, and it frequently experiences large ocean storms that are capable of flooding the lower elevation beaches and causing large, significant morphologic change. In my talk today, I will be focusing on the impacts of one such storm, post-tropical storm Teddy, that impacted Sable Island in September 2020. I will be focusing on an assessment of the freshwater resources on Sable Island and the impacts of this storm using two traditional monitoring techniques, including geophysics and monitoring wells, and discussing how this monitoring using these traditional techniques motivated us to develop a novel wireless monitoring system on Sable Island. We first applied transient electromagnetic geophysics to map the island's freshwater. Now, this sounds quite complicated, but it is a little bit more simple. We were able to apply this instrument, the ABM Walk 10, in various stations in a transect from south to north across the island, as indicated by these orange dots. At each of these dots, we performed a station that allowed us to get a representation of the island's water content with depth. And interpolating across the island between these stations, we were able to map the island's subsurface water conditions based on resistivity, where high resistivity corresponds to freshwater and low resistivity corresponds to seawater. We were also able to compare our results in 2020 to those of Terry Hennigar that were published in 1976 to assess if there has been long-term change in the island's freshwater resources and to try and determine what may be the driver of these changes. So our results are presented here and highlight that there is a significant fresh groundwater lens on Sable Island and that the fresh groundwater that is shown in blue here floats above the denser seawater that is in red, as I described earlier in my talk with that first diagram that I presented. Now, comparing our results from 2020 to those of Terry Hennigar in 1976, we can see that there has been a 5 to 10 meter contraction in the maximum thickness in the fresh groundwater lens on Sable Island at this main station transect. Additionally, if we look along the South Beach, there has been a complete loss in the southernmost dune on Sable Island, and associated with this loss, there has been a complete loss of the fresh groundwater lens in the first 200 meters of the island. This highlights that morphologic change and large erosion events that can impact the island's dune system have a significant control on the island's freshwater resources and the distribution of the island's fresh groundwater. It also highlights that morphologic change is a significant driver of vertical saltwater intrusion on Sable Island. In addition to those geophysical transects, we installed monitoring wells along this transect, as indicated by the red triangles on this diagram here. These monitoring wells were installed and instrumented with level, temperature, and conductivity loggers. And these loggers allow us to measure the groundwater response in level, temperature, and electrical conductivity, which is used as a proxy for salinity, in the groundwater in response to ocean conditions. So we were able to see in our data steady state conditions when the aquifer is not being impacted by storms in comparison to when the island's groundwater is being impacted by these large storm events that flood the beach. Initially in our data, we can see that groundwater levels were quite stable. The level is the data in blue, and the electrical conductivity is very low, indicating the groundwater that we were monitoring was fresh. In September 2020, post-tropical storm Teddy impacted Sable Island and caused a dramatic increase in the groundwater level following the storm. And it also caused the electrical conductivity in groundwater that we were monitoring to increase to the same level as that of ocean water, indicating that this fresh groundwater had been salinized by the large storm event that flooded the low elevation beach. In the months following this storm event, we were expecting the aquifer to recover to pre-storm values. However, in the months following, the island continued to be impacted throughout the winter by large storm events and nor'easters that caused subsequent incidences of salinization and prevented complete aquifer recovery. Finally, this highlights that aquifer recovery is prolonged relative to surface water flooding. Prolonged recovery in this sandy island and the short return periods of these large post-tropical storms events highlights that saltwater intrusion from these large flood events and morphologic change is a significant risk to the freshwater aquifer of Sable Island. So now moving on from the groundwater to surface water ponds on the island. In addition to the fresh groundwater, Sable Island has these small surface water ponds that are of a major concern for the island's ecosystem. Ponds on the island are of varying size and water quality, and these surface water ponds are found in topographic lows, which indicates that they are groundwater sourced. Because of the thought that these surface water ponds are groundwater sourced, it highlights a concern for these surface water features and the potential impacts of declining fresh water in the groundwater and the impact that that may have on surface water ponds. Observations of surface water flooding and significant morphologic change along many of these ponds has raised concerns about the risk of some of these ponds being lost from breaching from these large floods that could overtop dunes and salinize the freshwater resources, and morphologic change that could infill the pond or cause it blowouts to cause these surface water ponds to be lost. This is highlighted in this figure where you can see the proximity to these floods and the significant morphologic change that is occurring in some regions along the ponds. In addition, ongoing monitoring of the surface water ponds on Sable Island using monitoring wells and aerial satellite imagery has revealed that there's a significant decline in the volume of surface water ponds across the island. Many of the ponds have levels have inter and intra-annual variability, and there's observations of long-term declines that have been causing many of the ponds across the island to go dry seasonally or to be lost altogether. This figure here highlights horses that are gathering in a dry pond bed to drink from the remaining fresh water that they have access to. In addition, horses along the east portion of the island are observed to dig down to the water table to access fresh groundwater. because of the absence of surface water ponds in this region. Using remote sensing data from 2016 and 2018 in the wet and dry seasons, we were able to reveal that the ponds on Sable Island are very dynamic and have these inter and interannual changes. Green areas highlight that ponds in the wet season are significantly larger than ponds are in the dry summer months, highlighting how variable ponds are across the seasons on Sable Island. Comparing ponds between 2016 and 2018, we can see that these ponds that are found in the island interior are the ponds that are highlighted in blue and green, tend to be consistent or increase in size between years, whereas ponds that are found along the island's dune margins are more prone to being lost between images. This highlights that morphodynamic change and erosion of the dune system on Sable Island is a significant driver of pond area decline and emphasizes the important control that island morphology has on the island's freshwater resources. These observations motivated Dr. Barrett Kurlick, Dr. Scott Ketchison, and I to develop a satellite-based wireless sensor network on Sable Island to monitor real-time environmental data, including atmospheric data, surface water pond data, groundwater data, and ocean conditions. For the purpose of my discussion today, I'm only going to be focusing on the installation of a Campbell Scientific and Riot Technology wireless monitoring system that allows us to monitor the surface water ponds on the island and effortlessly share this data with Parks Canada managers and local stakeholders through a continuously updated near real-time website. The ponds that we are monitoring are located at the west side of Sable Island. This location was selected because it is one of the main pond complexes on the island, and because we had previously been monitoring 3 ponds here, so we have extensive data from this area. Additionally, these 3 ponds were selected because of their close proximity to the West Lighthouse, which was important for meeting the infrastructure requirements of the wireless sensor network. Additionally, we have long time series of data in these ponds, including stilling wells to monitor the surface water, monitoring wells at depths to monitor the connection between these surface water ponds and the groundwater, as well as some sediment temperature rods that allow us to monitor the temperature and the fluxes between these surface water ponds and the aquifer. So the network we installed is quite complex, but the general measurement process and data transmission process is described here. So I know this slide has quite a bit of information on it, but generally the process that occurs is every 30 minutes, our Campbell Scientific data logger that controls the system initiates the measurement process. The logger turns on and it initiates communication with 2 directly wired instruments. It first turns on a relative humidity sensor and a temperature sensor that make a measurement of the atmospheric conditions on Sable Island. It also turns on a gateway. This gateway controls our wireless sensor network and the measurements that are being made in the ponds. The gateway turns on and initiates communication with 3 motes. These 3 motes are located in the previously described ponds. And these motes then turn on the sensors that are located in the ponds. These sensors make a measurement for water level, water temperature, and electrical conductivity as a proxy for salinity. And then the data is sent back to the motes, and the gateway then integrates all the data that it received from all 3 motes and sends it back to the Campbell Scientific data logger, along with the data that we got from our atmospheric sensor. This data is stored in our Campbell Scientific data logger until it is transmitted via a satellite antenna to the GOES satellite system. From the GOES satellite system, we use the Campbell Cloud website in order to ingest and integrate our data every hour and make this data accessible in real time on our website. So our website is www.dal.ca/hydro, and from our website you are able to access our Sable Island page, which provides a bit of background on Sable Island's ecosystem and the wireless sensor network that we are setting up on the island. It includes some initiatives about ocean monitoring and some groundwater monitoring, but for the focus of our talk today, it focuses on our wireless pond monitoring at West Light here. It allows you to access our Campbell Cloud dashboard through the highlighted link on the website, which brings you to our Campbell Cloud page. On this page, you're able to access data, including real-time wireless pond water levels, pond temperatures, and electrical conductivity. Through monitoring this data, we are able to monitor through long-time trends in the 3 ponds water levels. We're allowed to able to monitor for daily and seasonal trends in pond temperature, and we are able to monitor pond electrical conductivity. Using this Campbell Cloud, we have set up alerts so that we can notify Parks Canada managers if pond water levels become incredibly low, indicating that the pond is drying up, or if there is large spikes in electrical conductivity of the pond, which may be indicative of one of these large flood events breaching the coastal dune and salinizing the ponds. Although we initially had great success installing this system, and this system is incredibly well suited for Sable Island because of the remote nature of the island and the wireless capabilities of the system, we have had many challenges with protecting our infrastructure from some of the extreme conditions that are present on Sable Island. This includes high moisture conditions from the maritime climate that has caused some electrical issues in our moats, high winds that like to bend our moat antennas down, as well as itchy and curious horses that like to rub on our moats, which could disturb them. So we've had to install some protective structures. In addition, some of our early data transmissions indicated that there were small data gaps in our continuous data. We've had many challenges with accessing the site to perform ongoing repairs for this data in order to get more continuous data. And ongoing work has to be completed in order to update this system and provide more continuous data and update the cloud website. Currently, our cloud website is not transmitting data because we've had some challenges with moisture in our moats, which have had to come back in for repairs, but they will be reinstalled in the early spring of 2022. And we hope to resume continuous data being updated on our cloud website. So in conclusion, Sable Island hosts a very unique ecosystem that is faced with challenges due to the dynamics of the island's freshwater resources. To better understand the challenges facing the freshwater resources, we conducted surface and groundwater monitoring and installed a state-of-the-art wireless sensor network to monitor the water quality and the water quantity concerns of the freshwater ponds on Sable Island in near real time. In the future, we are working to expand this wireless monitoring system in order to include additional environmental conditions, such as potentially more ponds, groundwater conditions, and wave conditions using offshore wave buoys. Doing so, we could provide a more holistic understanding of the groundwater and surface water conditions and ocean conditions that are impacting them on Sable Island. Finally, future work and the future directions of my PhD is to apply this monitoring data to develop and assess numerical models that will help us assess climate, ocean, pond, and aquifer interactions, and to model these situations in current and in future climate conditions in order to understand what the drivers of freshwater vulnerability are on Sable Island are now and in the future. And with that, I would like to conclude my presentation. I would like to thank the Friends of Sable Island for providing me with the opportunity to talk today. And I would like to thank all of the funding bodies that have supported this work, including the various scholarship organizations that support me, Neopar that has supported our knowledge mobilization grant to install this wireless sensor network, and Parks Canada, who have supported us with many flights and on-ground logistics to install this system. Finally, I would like to thank Barrett and Scott for all of their hard work in the field installing the system. And I look forward to taking questions in the discussion period to follow.
Great. Thank you so much, Julia, for your important research on the freshwater resources of Sable Island and for sharing it with us today. It is indeed critical to understand the impacts of climate change and human presence on the future of this island. For those watching the recording, if you enjoyed this presentation, please consider a small charitable donation towards our scholarship program. For those attending the live session, we will stop recording now and take some questions.